let's look at more radical expressions and how to simplify them. So first, let's look at adding and subtracting radical expressions. 7 radical 5x plus 8 radical 5x. Here, the radicals are identical. They have the same index, they're both square roots, and what's underneath the radical is identical. So these we can combine together by adding the 7 and the 8. 7 plus 8 is 15, so we have 15 radical 5x. 11 fifth root of 4x minus 8 fifth root of 4x. Again, here, the radicals are identical. They both have the same index, 5, and what's underneath the radical is identical as well. So here we can subtract 11 minus 8 and get 3 fifth root of 4x. Let's look at simplify before we add and subtract. Radical 12 plus radical 75 minus radical 3. 12 we can write as 4 times 3, so we can rewrite this as the square root of 4 times 3. 75 we could write as 25 times 3. Remember, we're looking for the largest perfect square factors of these numbers, and the largest perfect square factor of 75 is 25, just like the largest perfect square factor of 12 was 4. So we have plus the square root of 25 times 3 minus radical 3, because that cannot be simplified anymore. We can separate the radicals. So we now have the radical of 4 times the radical of 3 plus the radical of 25 times the radical of 3 minus radical 3. Let's simplify the perfect squares. Square root of 4 is 2, so we have 2 radical 3 plus the square root of 25 is 5, so plus 5 radical 3 minus radical 3. Now our radicals are the same, so let us combine what's in front. We have 2 plus 5 minus 1. So we get 6 radical 3. Okay, let's look at more simplifying radical expressions. For example, with variables, the square root of x to the 8th, y to the 12th. So we can write x to the 8th because we have a radical, a square root. With index 2, we want to write this as a square of something. So I could rewrite x to the 8th as x to the 4th squared, because the power rule says a power to a power, multiply your exponents. So you can see how if we simplified that again, we would get back to x to the 8th. Y to the 12th can be written as y to the 6th squared. So now we can combine those two expressions underneath the radical into a single perfect square. The square root of x to the 4th, y to the 6th squared. The radical cancels out with the square, although we do need to make sure we have the absolute value because we want a positive value, so x to the 4th, y to the 6th. And because x to the 4th is always positive and y to the 6th is always positive, we can drop and not need to continue using the absolute value bars. So our problem here simplifies to x to the 4th, y to the 6th. Now let's look at a slight variation. What if it were the square root of x to the 8th, y to the 10th? So I changed the exponent on the y term. Well, following the same steps, I can write x to the 8th as x to the 4th squared. Y to the 10th, I can write as y to the 5th squared. Again, we're looking for quantities we can square because we have a square root. Combining them into one perfect square. Square root of x to the 4th, y to the 5th quantity square. When we take the square root, we get the absolute value of x to the 4th, y to the 5th. X to the 4th is always positive, so I can drop the bars around x to the 4th. But because y to the 5th has a odd exponent, we do need to keep the absolute value bars around the y to the fifth. So this simplifies to x to the fourth absolute value of y to the fifth. So two properties we do need to remember. Radical a times radical b is the same as or equals radical a times b. Radical a divided by radical b is equal to the square root of a divided by b. So let's use these properties in some examples. Oh, by the way, when we're dividing, remember we cannot divide by 0 because it's undefined. So here we would need to make sure that b does not equal 0. Example 4, multiplying radical expressions. So let's say we have the square root of 8y to the fifth times the square root of 50y cubed. Let's use that first property that start above and combine them under one radical. So the square root of 8y to the fifth times 50y cubed, we can simplify that. 8 times 50 is 400. Y to the fifth times y cubed. Our exponent laws say we add our exponent, so I have y to the eighth. So 400y to the eighth is underneath our square root. Let's see if we can write both of these as perfect squares. 400 is 20 squared. Y to the eighth can be written as y to the fourth squared. So now I can combine them into one perfect square. The square root of 20y to the fourth squared. Taking the square root of 20y to the fourth squared, we get the absolute value of 20y to the fourth. 20 is positive. Y to the fourth, because it's raised to an even exponent, is also positive. So we can drop the absolute value bars and have 20y to the fourth. One last example. Let's look at dividing radical expressions. The square root of 18x to the fifth divided by the square root of 2x cubed. Let's combine these using that second property on the last slide and we'll combine them into, so it's a fraction underneath a single radical. The square root of 18x to the fifth divided by 2x cubed. Let's simplify that fraction under the radical. The square root of 18 divided by 2 is 9. X to the fifth divided by x cubed, we need to subtract our exponents. So we have x squared. So now we have the square root of 9x squared. Let's see if we can write both 9 and x squares as perfect squares. 9 is 3 squared. X squared I can write as x squared. Let's combine them into one perfect square. So the square root of 3x quantity squared. When we take the square root of 3x squared, we'll get the absolute value of 3x. But here, because in our original numerator and denominator, we had radicals with odd powers of x underneath them, we know that x has to be non-negative. In fact, it has to be positive because we can't divide by 0. X has to be non-negative because we would not have a real number if we were taking the square root of a negative quantity. So because of that fact, here we can drop the absolute value bars and we have 3x.